the work we have done recently on AI. Okay, this is so recently we have been a little bit involved in AI for materials, and yeah, that was sort of an interesting collaboration, and that also caused us to think a little bit about AI and what to do with materials. And basically, so if you think what is the main premise of AI, it is if you have enough data, you really don't need the expertise of experts. And there have been extreme successes in that, like protein structure, medical images. And the underlying idea is you don't need to be a medical doctor, you just need to be trained on a lot of data. And similar with playing games, chess and Go, or languages, that you don't need to know the grammar to be an excellent translator by just learning from examples. So then an interesting question is, can you do, and that's of course, can you do the same with materials? And this one got a lot of attention, and that is from Google DeepMind. And they put literally in their article, our work represents an order of magnitude expansion in stable materials known to humanity. And that's interesting because these were inorganic materials. And if you talk with inorganic chemists, they're actually surprised because they have, going back to Pauling, they have the Participant theory that basically says nature is surprisingly boring in inorganic chemistry. It has some well-known motifs that are coming back again and again. So if you tell to an experimental inorganic chemist that you have discovered an order of magnitude new materials, they will be very excited because that hasn't happened. It's difficult experimentally to come up with a really new material. So Tony Cheatham, he is one of those inorganic crystallographers. He basically looked at that work and thought about it from that's interesting. So let's first show his main argument is if you look at inorganic materials, you'll have things like niobium and hafnium and zirconium, and those metals are very similar that every inorganic chemist knows that you can exchange them. So for example, what they did is they selected 10 new materials and try to identify whether those materials were truly novel. And this is then a typical example where you can already see that the main difference is this green dot here in the crystal structure. And that is typically one of those elements you can easily exchange. So for a inorganic chemist, this is not really a new material, but more problematic is it will also be very difficult to synthesize them. You can easily do that on a computer. You can put them on those crystallographic positions, but getting there experimentally, since the metals are so similar, it will most likely be a random distribution. So the other things they were observing is that, if you, these were based on DFT calculations, and if you increase the temperature higher than 0 Kelvin, you can have transitions, symmetry, and that's not a new material. So of the 10 randomly selected materials, they were basically saying they were not really truly new. But the point I would like to add is that what they were doing in say Google DeepMind, they were mainly enumerating compounds. And it was trained to the materials project, which was basically also augmented with computational data. And the argument that Tony Cheatham was sort of making is if you really go from compound, you can only call that a material if it has some usefulness. Just enumerating compounds is a very good starting point. but it's not really a solution for a material. And for example, what they then sort of illustrated, if you make compounds with these elements, they are trace elements in the uranium ore. So making new compounds with those materials and trying to make them useful will be an extreme form of chemical interest, but very unlikely that it will actually be useful. Yet there were about 80,000 novel compounds with those materials. So really the argument they make is you're enumerating compounds, but you need to show some practicality before showing some materials. And why is that important? So why is this? And I think that is the point I would like to make. If you want to do machine learning in chemistry, you always have a problem of compared to the previous playing Go languages, you have an enormous amount of data. But if you want to go from a compound to a property, there, or let's say an application, there you always will be in this limit of low data. So you need to have a strategy to augment the data, generate more compounds. And the other thing is, if you need to augment, you also need to have ideas of what type of properties you need to calculate in order to be relevant for a particular application. And I will get back to this. So the view we have is you need a lot of domain knowledge to know what properties are important for a particular application, and you need to know the domain knowledge to be able to augment the data, that you have enough data of your application of interest to train an AI model. Then the other practical thing is, since you augment, the most likely materials that have stopped performing are generated in silicon and haven't been synthesized yet. So you also will need a strategy on how to synthesize these materials. And that is also something which is still very far from just enumerating possible stable materials. Okay. So where are we interested in? And that is basically, in Europe, you can't vote climate change away, but so I'm coming from a part of the world where it's still an issue. And that is, we have sources of CO2, and we have sinks of CO2. And the question we have, can we identify an optimum way of connecting? Can we identify an optimum separation? And where we then are interested in is basically what is if you have a given sink, and what is actually important here is that the concentration of CO2 is varying a lot. And here what is important that you need to deliver your CO2 at a specification that is very different, depending on which mineralization you can do with a much lower CO2 concentration than, for example, for fuels. Okay, and the materials we're interested in is a metal organic framework, but really from this perspective, can you tailor-make a material that is optimum for carbon capture? And since you have so many materials, it's sort of a class of materials where AI, machine learning is sort of an obvious choice to work on. So for those of you who didn't notice that Nobel Prize was given to metal organic frameworks in Berkeley, these materials are porous and you have an extreme tunability. So the question we have, can you put every atom at exactly the right position to capture CO2? And many people in Berkeley are working, including Jeff Long or Yagi, on these type of materials. Okay, so if you think about it, and this is a topic that I was really interested in when I was here in Berkeley, and I started to work on that. And Jeff Long and I, we were working together on an EFRC, the Energy Frontier Research Center. And the interesting thing is they are supported by the Department of Energy, Basic Energy Science. And program managers at Basic Energy Science, they have a long-term horizon, so meaning 15 years and longer. So if you threaten to do something useful, they get nervous. So we were comfortably working on our planet here, working on these type of materials, where basically in the introduction it was said, I have a background of chemical engineering, meaning I probably have some books somewhere on chemical engineering, and I can open them and read the first paragraph and say, okay, selectivity is important. So we were doing quasi-intelligent things about what is a good material. The chemical engineering community, on the other hand, they use very different words like capex, opex, costs, and those kind of things. And you see they're comfortably looking at the other side. So if I went to a real chemical engineer with a metal organic framework, they were like, how many kilograms can you give to me? And they said, well, on a good day, a few milligrams per PhD student per day, and not interested. So you typically see that on this side, we have many materials with some vague ideas of what is important, but on this side, they're not interested in. And then coming back to these materials. So here, on this side, about 15,000 porous metal organic frameworks have been synthesized. And if you sort of look for how many materials do we have enough data, we can go here to this side, that it can design a plant and calculate whether it's a good material, maybe one or two. So you already see the enormous gap you have between what is known at this part and what is needed for a particular application. And these are the simple things we don't routinely measure, like a heat capacity or something like that. They're just things that are needed. So what we try to do, and that is a project where also Berend was involved, it's called BIDMaP, where we try to bridge the two. Okay, so how do we do that? And that is basically, we created this BIDMaP platform where I live on this level, and that is basically from the crystal structure, I try to predict properties of metal organic frameworks using DFT, molecular simulations, whatever I can get my hands on making predictions. But the predictions are sort of dictated what the chemical engineers need to know for their process design. And then if you do a process design, you typically have the amount of material you need to capture. That's more capex, but you also have the energy costs. And you need to, if you want to optimize this problem, you need to be able to weight the two. And the way we weight the two is basically by doing the techno-economics. And that is basically what is the cost of electricity, what is the cost of steel, what is the cost of making them off. And in that way, you can come up with an objective function to optimize because you can weight the two. And then finally, what we also do is a life cycle assessment. And for that, it's for example, important that you make a material that captures more CO2 than indirect emissions caused by the synthesis of the material. For example, if you capture with a coal-fired power plant, you lose efficiency of your power plant, and the grid needs to compensate. With this compensation, CO2 emissions are associated, and you need to discount that. And that is then something we do with a life cycle assessment. And that is a collaboration with many different groups. And we published the results of that a year ago. And just to give you an idea of how that works, so at the materials layer, you can have molecular simulations or experimental data, and you have this enormous data flow with databases, what you can do. And at the end of the day, every layer gives a key performance indicator, which you can look whether that is optimum. And here we have selected a few for the materials layers, the selectivity, process layers, purity, productivity. This is a cost, which is typically where people are interested in, and you have something on the life cycle assessment. And what is shown here is a ranking of the top performing materials in terms of their KPIs. So a line is a material, and here these purple ones, there is the top 10 in terms of selectivity. So if you follow this material, and that is sort of the importance of this message, you see that the top 10 ends up on the bottom in terms of cost. So, and there you already see that these simple metrics from just looking at the selectivity as a proxy for a top-performing material is not always working. In this particular case, it's not working at all. Of course, and you can do the same trick with the other key performance indicator. And here, where we then looking at is the net carbon avoidance cost. So here we have a reference. This is a cement. This is in a cement plant in the UK. We also make this region dependent. For example, what is the cost of electricity? But for example, if you're interested in direct air capture, the climate is also a very important. So you want to look at these kind of things. So here, this is an MEA. This is the state of the art. Say, if you want to build a carbon capture plant tomorrow, this is what you would get in terms of cost. And you see many materials that outperform the state of the art, and this the same in purity. Okay, so what is then, of course, interesting is if you do these screening studies. So we selected about 1,000 metal organic frameworks. You can't screen for everything. For example, long-term stability, whether it's easy to make, whether, for example, it's stable in water, and all those kind of things. So what we do is we generate a set of top-performing materials, and then hopefully somebody on the experimental side, like would be interested in making that. But we would like to make sure that we have as many options as possible. So what you also have seen is what we do is we do molecular simulations, we do DFT calculations. It's faster than experiments, but it's still very time consuming. So we screen of the order of 1,000 materials, and we would like to go to a much larger database to be able to get many more candidates than the 30 we had. And of course, if you then do this, and what we have here is this net carbon avoidance cost, which we want to optimize, meaning as low as possible. Here we have the percentage of materials that have a net carbon avoidance cost higher or lower than that. So here we are about 50% of the materials have a net carbon avoidance cost less than 100. And what we want to do is we want to get as many of those materials, but we know very well how a bad material looks like, but not so well how a good material looks like. So what do we do is how we then do it in an iterative way. So we start with saying we make a classification model where it has as input the crystal structure, and then we try to predict whether it has an NCAC, let's say less than 100. And that's then the first step. And then we do that, and then we evaluate the material using DFT, and in that way we get more and more top-performing materials, and then we can lower the cost and do that again. And that is the way we look at that. So this is our initial database, and I will get back to that later on how we selected this database. And you see we have an equal distribution of materials among all costs. But we then trained this classification model, and we started with 105, and then we generate materials with this distribution, where the width of this violin plot is the number of materials with these costs. And you see we can now decrease, and you see we get more materials with a low net carbon avoidance cost, and in total we could add 130 materials, and that is a way we do AI-driven materials design. So what you then can also do is you can inspect where are these materials in the chemical design space. And what we do here is we do these typical UMAP diagrams where a dot is a material, and this UMAP has been trained that if materials are similar, they have a similar net carbon avoidance cost. And they plotted close by. So what you see here is the green ones. This is our original database. You see it's a bit spread over the entire chemical design space. Here are the materials where our model predicts it's less than 105. And you see here you have a region where there are only 4 materials, and we didn't even sample them, and those materials are non-porous. So what you see here, if you then make the net carbon avoidance cost smaller, you start to zoom in particular regions of the design space. And you see here, it's you have materials that are very good, and you have materials that are very good in here, but they're still far apart. So apparently, for different chemical reasons, you have a good material, and it would, and if these UMAPs would, if the underlying descriptors would be better interpretable, you could go back and inspect what makes this, what characteristics is that for a good material. Okay, so so a few things where we were using AI in this approach, and in particular where we do not have real knowledge about things, and that my son forced me to include that. And he said, you give a presentation in Berkeley, and you assume they have no understanding. So make clear it's your understanding because you put the bar really low. But anyway, so what we have shown here is a shortcut model where you actually go from the crystal structure to the net carbon avoidance cost. That's one way where we're using machine learning. But we have been doing a few other things like the force fields, and also something on synthesis from how to make these MOFs and what you can do there. So I would like to talk a little bit about those two topics. And improving force fields, and this is a sort of, if you do these screening studies, you use a classical force field to predict the adsorption isotope. And that is how much CO2 gets adsorbed in these materials. So what you see here is the experimental CO2 uptake and the simulated CO2 uptake. And if you would have perfect agreement, it would be along this line. And what this is showing is that these materials, these are different MOFs with aluminium, they're really performing very poorly. And what you see here as well, if you calculate the binding energy with DFT, you get this signature that the DFT binding energy is really off from the binding energy you would get from your classical force field. And this is well known because this is the universal force field we're using, and it's really performing very poorly if you have aluminium. And and I had a PhD student who was a bit stubborn, and he said, I can repair that. And you typically, what the problem is with force fields is you improve it here, and then it fails there, fails here, and you improve it there. So it's almost a vicious circle. So I really was very hesitant from, don't go there. And of course, he didn't want to listen, which I think is a good thing. It could be a Berkeley student. He really was very, very successful because after his tuning, he really got it right. So that was interesting. And but he really got annoyed with this MOF. So this is an aluminium MOF. It's done in the Paris group. So here are the experimental data. This was the original UFF, and this was his model, and it's still very far from the experimental data. And that was one of the MOFs that really, really failed. And this is another interesting graph. So if you look at the Prisma model, and if you look in the engineering, you will see we do indirect heating, meaning we have a tube and we put steam in the tube. What is often done in practice is you heat directly with steam to regenerate. But for that, you need to know the adsorption isotope of water. And our models are really bad for water. So what you see here is the model we were using for CO2. Here you have the binding energy from a force field, here from DFT. And you see it's not perfect, but you can rely on it a little bit. This is water. You see the binding energy from a force field and the binding energy from DFT is really off. And these are enormous real errors. So why is water so difficult to simulate? So what you can do, and that is a very interesting approach, there is now those generative force fields. So what, and it's again an example where they used the materials project, where they trained a machine learning force field on all the data, on the DFT data of the materials project. And there are now many, I think most of the big tech companies have one, but this is the one of Cambridge, the MACE force field, what we're using. And since this is the equivalent of a universal force field, but now trained on DFT data, so it's interesting to see whether you can do useful predictions. And so what we try to do here is take that mace force field out of the box, try to predict the heat of absorption, which you can measure for water in the metal organic framework. And what you see here, it's in this mil 160. So this is the value you get if you take it out of the box. And you see it's 10, experimentally it's 50. So you really see, but this is a difficult calculation because you calculate the heat of absorption by doing a simulation of water in the metal organic framework, and you do a simulation of the metal organic framework, and you need to subtract the two. So you have two large numbers. So the requirements for accuracy is typically much more than what you see in these leaderboards. But what you can see here is if we add training data where we fine-tune the model, we can get to the experimental value. So what is the strategy? What we need to do is we need to fine-tune the model. We need to add some DFT data to get it right. And of course, these DFT data are really expensive. So it's really about how to optimize, how to minimize the number of DFT calculations. And and this is also some type of research which we can only do in Europe, because the key parameters we do is look at diversity and affirmative action. So why is that so important for this problem? And but first, let me start with where we came about this idea of diversity, and that is these are the number of synthesized MOFs in the Cambridge structural database. And if you have such a large number, you can always wonder, how about the next new material? How different is that from the previously formed materials? And how do you differentiate in chemistry materials? So this question is, how novel is the next MOF that is being synthesized? So the way we do that is basically we do a featurization of the MOF in terms of metal chemistry, functional groups, linker chemistry, and pore geometry. And then you have a measure of distance, how different these metal organic frameworks are. So here we then collected all the databases, the experimental databases and the databases from hypothetical predicted MOF structures. And we then we make these UMAPs where we looked at the crystal density here. So here the density is lower than here, and here is how if the material has large pores, and here it has large pores, and here it's relatively dense. So what you then can do is you can, if all the dots are, all the material, all the databases combined, and then you can sort of see how are the different databases, how diverse are they? So what we look here at the green ones, those are the experimentally synthesized MOFs. And how diverse are they in terms of their pore geometries? And then you can sort of see, interesting, that they are very largely sampling this region, but this is relatively sparse. And these are two, let's say, in silico generated MOFs, structures where people generate structures in silico. And you see this database is mainly sampling this part, and this database is mainly sampling this part. So what we then did in this Prisma database is made sure we had the entire coverage of all the database by selecting a set of diverse structures. So what you then also can do is then you can say, hey, here, this is, if you then look at all the pore geometry, you see we cover it quite well with our hypothetical database. Here you have the linker chemistry. You see you do it a little bit less. Here there are some linkers that are, now the gray dots are the ones that are in the core MOF in the experimental database. But you sort of see in the metal chemistry, we're really doing very poorly. And the reason is very simple. We don't have a theory of how to predict a new metal structure. So what you typically do is you harvest the metals from the metal nodes from the experiments, and then you add linkers to it in those databases. So in order to make it then more diverse, we basically harvested more of those metals and generate a library with a more diverse metal base. So for us, it was much more important to look at a diverse set of structures rather than at a large number of structures. Just it's important to keep that in mind. And what you can let's sort of see how different in pore geometry MOFs evolution of how different the pore geometry is. And you see the research focus on similar structures, and then once in a while you see that jumps are made in this graph. And then it's interesting that you can do some archaeology, and you can sort of say, okay, what are those structures that are so different? And here was the first MOF of Omar. And you see before there have been structures that posteriori have been declared to be metal organic frameworks. And you see some of those peaks are really very different structures. So you can really say, oh, okay, that's interesting. Now a completely different class of MOF have been appearing. Okay, so why is that important in the context of this fine-tuning? So what you typically do with these force fields is you run a simulation. You do a molecular dynamics simulation, but that molecular dynamics simulation is done with a force field that is not sufficiently accurate. So you need to fine-tune. So what we then typically do, and that is you start a simulation, and that is this part of the red dots. Then we select, say, 200 most diverse configurations, for which we then do a DFT calculation. You add that to the training set, and you fine-tune. Then what you do is those active learning rounds. So you continue your molecular dynamics simulation, but now we have 4 different machine learning models. Hey, you train them with different random numbers. So you have a measure of the accuracy. So if the 4 machine learning force fields disagree a lot, then you say, okay, it's not sufficiently accurate. We need more training data in this region. And that is sort of illustrated here. This part that are configurations that have a high accuracy, and in this part the accuracy is poor, and you see that. And then we again use the same idea. You analyze the diversity of your configurations, and then you try to, with quite a small number of DFT calculations, cover that space. And then you update, and you do that until you're really happy with the accuracy of your trajectory. Okay, why is that important? And that is, for example, if you don't evoke that, and that is what most previous studies do. For example, you sample your configurations at random for which you do a DFT labeling. So what you then typically see is you sample the most common very frequently, but that contains very little information because they're all the same. What is really important is that you also sample the barriers. And for that, you really need to do some affirmative action. You really need to go out of your way to make sure that those rare occasions that you actually label them with DFT, because otherwise, yeah, if your barrier is not correct, you may not sample the dynamics that is behind that barrier and those kind of things. And what you then can actually see is the number of samples you need to have to get a similar diversity is an order of magnitude larger. So yes, you can do it by brute force, but you pay an order of magnitude more. Okay, so now a few interesting things you can do with this. So typically, what is done in these type of calculations is you do an energy minimization. You get, for example, the QMOF database, which is part of the materials project. They generate a structure and they optimize with DFT. And that is the starting point. So what we did is with the machine learning force field we trained, we follow the dynamics, and you suddenly see a phase transition. And the reason was that all the hydrogen bonds rotated a little bit collectively, and that caused a much lower energy configuration. So then what we did is we identified the lowest energy configurations on our trajectory, energy minimize, and then compare that energy minimum with the original DFT minimum. And what you see here is all the corrections we needed to apply to get really to the true minimum energy. So basically, this method of training a force field very efficiently is really very powerful, because if you do an energy minimization, you do many DFT steps, but they're all very correlated. So from a machine learning point of view, you don't learn anything. So you're much better off thinking a little bit, how can I use those DFT calculations much more effectively to address these problems? Okay, quickly. It's really impressive, the improvement you can get. These were the experimental data with the classical force field. This is now with this fine-tuned model. We really get the heat of absorption and the Henry coefficients correct. And also this one, the annoying one. So this is now the absorption isotherm, and it agrees really well with the experimental absorption isotherm. And what was actually going on? And that's also the reason why water was so difficult. So what you see here, this is the CO2 molecule. Here are those hydrogen bonds. So it optimally forms 4 hydrogen bonds in the minimum energy configuration. But as soon as you have some thermal motion of the hydrogen bonds, it loses that optimum configuration. So this one, this very high absorption, is done with a rigid crystal structure, where by accident it was optimally for the CO2. And of course, the force field was correct, but we didn't take the movement of the hydrogens into account. And that is the reason why it drops so much. And also why water is so difficult to simulate. It's not very large vibrations, but it's simply small orientation, changes in the orientations of the hydrogens in the metal organic frameworks, which you really need to capture, and you can capture that very well with those machine learning force fields. Okay, so the final topic, and that is about the work we have been doing experimentally. And so when I moved from Berkeley to EPFL, how do I say that? They give you a lot of money, and I didn't know really, I didn't have so many ideas. So I needed somewhere where I could spend money. So I started an experimental focused on synthesizing MOFs. And what became very clear to me is if you have a PhD student that's making those MOFs, they get better and better. And then they graduate, and you can start over again. So what is it that they learn while doing these experiments? And they call it chemical intuition. So and we became interested in, can you capture that? Okay. So we started simple, and that is we looked at this H-cust, and that's a metal organic framework which you can easily synthesize. Even we could do it. But the interesting thing is, this is all the synthesis that is reported in the literature, and they measure the surface area, and the color coding is different experimental techniques. And what you see is, depending on who made it and which experimental technique, the surface area is very different. Well, the surface area is a bit of a strange number, but the advantage of these kind of things is I can say my number is bigger than yours. And that does well in science once in a while. So the question we have, can we get the biggest number? And the way we did that is we had a robot to synthesize this. This was living in 9 dimensions. So how do you sample that? So what we wanted to do is really a sort of an unbiased sampling. So the very first thing we did is, how do you initiate that? This robot with 30, again, most diverse samples. So what we did is, you have the experimental conditions, you define you scale the experimental conditions from 0 to 1. And then you measure the distance between 2 points. And if the distance is close, the experiments are similar. If it's far apart, they are very different experimental conditions. And then what we started is we selected a set of 30 most diverse conditions by doing a min-max algorithm. Hey, you select one condition at random and the other one furthest away from it. And then the third one is the maximum minimum distance. So what is where can you put it that it's as far away as this one and from that one and the fourth? If you then look at that at very high dimensions, and you make and this UMAP is basically a projection on 2 dimensions of these distances, but in such a way that you want to maintain as optimally as possible if 2 points are close, they're similar. And in high dimensions, the set of most diverse conditions are at the edge. So this is sort of showing that. Okay, then the next thing we did is a genetic algorithm. And the basis was the following. We went to the experimental person and we asked the following question. On a scale of 0 to 10, how happy are you with yourself? Like a doctor. 0, shitty, 10, the best ever. Okay, then you had those samples, and then we organized a bingo. And the bingo was the following. Depending on the happiness, you could either get 0 poles with the experimental conditions, or say 10 of those poles. You roll it and you draw parents. And then you do these typical genetic operations. And what you then see is it's improving in this time the happiness or the crystallinity. And if you see what's happening, hey, you start to sample the interior, and on the yellow points, we were very happy, and we did the BET surface. And what you could see is, depending on the experimental conditions, there was a large variation, and we got a very large number. And basically what you see, something was happening at the surface. We had no idea what, but this one had the highest BET. And okay, so now what you then typically do, you say, I have the biggest number in the world, and you declare victory. And we now have 41 successful recipes. But what we also have is 200 failed and partially successful experiments. So what we did is we made a machine learning model that correlates the experimental conditions to the happiness. With the idea, if you use genetic algorithms, it converts very slowly. So you don't want to do that experimentally, but you want to do that with a machine learning model and then do the experiments less frequency. But anyway, what you then have is, if you do a random forest of decision trees, you can basically identify what are the most important factors in the happiness. And typically the concentration of water and a few other things. But this is typically the information that experimental people don't write down, but they keep in the back of their mind. Oh, last time I changed the temperature and a lot happened. So next time I sample the temperature more frequently than, say, the speed of the rotor or the speed of the heating up and those kind of things. So the way you can actually use that is, this was the synthesis of zinc H+1, and we were also interested in copper H+1. And then, of course, you can do the following experiment. You can say, okay, let's mimic my position, no clue. So you start with the set of most diverse conditions again. Or what you can do, a very careful literature search and actually go to the conditions that were optimal for copper. Or what you can do is you can say, oh, okay, let's now use my chemical intuition. Let's now sample the design space, but not with every parameter, experimental parameter, equally important in our distance, but let's weight it with the relative importance, which I got from my previous experiment. And in that way, you can actually see, so the red dots is without the importance, and the green dots, if you sample taking into account your previous intuition, and you see you just go much quicker into the interior. And it's also this idea that chemistry is very specific. So it's very difficult to copy the exact conditions. However, that's why the students get better. You can take with you the intuition. So the idea that you make a machine learning model from learning from failed and partially successful experiments by just probing this relative importance and how this importance depends on all kinds of factors. That is really interesting. The only problem is, of course, these failed and partly successful data never get published. And I do think that there is a lot of things to be learned if data gets more systematically published, failed and partly. On the other hand, you also have to realize that if you do these experiments, and after 100 experiments, you finally have your sample, you don't want to spend 99.9% of your time documenting all the things that failed. So that really also requires an infrastructure where it's really easy to publish these kind of things and doesn't become a real burden. But I do think there's many interesting things to do there. Okay, so coming back to the initial one. So I sort of hoped that I convinced you that I'm not against the underlying idea of machine learning, that with enough data, you don't need the experts. But since we don't, awaiting that robots and all those kind of things deliver more data, yeah, I have to admit, we go to this poor man's AI where you use knowledge and insights. And in that way, I would argue working with AI just make the experts better. And with that, thank you very much.
Thank you, Berend Smit, for that amazing presentation. I think we have maybe for one. You can give the same.
Thank you so much for the nice talk. I was curious, I guess, on one technical point and one slightly broader point where you've defined this UMAP in order to understand where different configurations are clustering. So I was curious in the context of MOFs, like do you have to think hard about how you define the distance metric that goes into this UMAP, in the space of these MOFs and their configurations? And then, I mean, you outlined this very kind of broad framework for integrating this with kinds of the needs on the industrial side, and combining with different sources. And so I was curious if you've looked at some of these combinations in those kinds of representation spaces, and if there are any insights on different materials that work well for one thing.
So for really interpreting those UMAPs, you need descriptors that are more easy to be interpreted than the ones we have. We were using RACs, those kind of things, and they're really difficult to interpret. Just from a tactical point of view, of course, if you look at similarity, similarity always depends on the context. For example, if you want to identify similar bridges, it really makes a difference whether you're a captain of a ship or a road repair person or a painter. You would classify similarity. So what we do in making the constructions, it's more how do you weight the different descriptors in measuring the distance. So what we typically do is we identify the top 7 of most relevant descriptors and then make the UMAP with the relative weighting of the top 7. So it's not the measure of distance, but more the weighting of the different descriptors we look at. And there was another question.
I was just curious if you've looked at these in the.
Yeah, we want to do that, but it's really a bit with the descriptors. We need to train it slightly differently with different descriptors that are more easy to interpret.
Thank you. Let's thank Professor Smit one more time.